Hi everyone, today we're going to be doing more Fibonacci examples. And here we're going to start this example off with a fact, which is if we make a list of any 4 consecutive Fibonacci numbers, so 4 that appear in order in the sequence, the first one times the fourth one is always equal to the third one squared minus the second one squared. Okay, we're not going to prove this, but we are going to use it, and it's kind of a mouthful. So what we're going to do first is verify this for a specific list of Fibonacci numbers. Okay, so there's 4 consecutive, right? They appear 8th, 9th, 10th, and 11th in the sequence. And what we've got is the first one times the fourth one. Well, here is the fourth one and the first one. So first one, which is F8, times the fourth one. And we're going to verify this fact. So we want to check, is that equal to the third one squared? So here's the third one, F10 squared, minus the second one squared. F9 is the second one, F9 squared. Okay, so let's remember what our Fibonacci numbers are. We need to go all the way out to 11. So we've got 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and I believe that is the 11th one. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so what we want to do is check F8 times F11. And here is F11. And 10, 9, 8, here is F8. All right, so we want to check that 21 times 89, is that equal to F10 squared? Well, here's the 9th one and the 10th one. F10 squared is 55. And minus F9 squared, well, that's 34 squared. We want to check that those are equal. All right, so 21 times 89 gives us 1869. And we want to know, is that equal to 55 squared, which is 3025, minus 34 squared, which is 1156. So let's do the difference of those. And we see that it is, in fact, 1869. So we just checked both sides of the equals in this fact here for this specific list, and we found that it was true. So we verified it for these 4 Fibonacci's. Okay, now we want to use the general list, right? Fn, Fn plus 1, Fn plus 2, Fn plus 3, and write this fact as a mathematical formula. So all we're going to do is the same thing we did up here, right? The first one times the fourth one, only now instead of specific numbers like 8 and 11, we just have a general, well, it's in the nth spot in the sequence and the n plus third spot in the sequence. Okay, so let's recall it was the first one, which is Fn, times the fourth one, Fn plus 3. And that is going to be equal to the third one squared. Well, Fn plus 2 is the third one in this sequential list, minus the second one squared, Fn plus 1 squared. So this is how we would write it out as a general mathematical formula. All right, let's go ahead and move on to another topic, which is Fibonacci-like sequences. Okay, a Fibonacci-like sequence is similar to a Fibonacci sequence, and the way that it's similar is it's still a sequence where the next term is obtained by adding the previous 2. So it's Fibonacci-like because you get new terms in the sequence the same way. Just take the previous 2 and add them together. And where it's different is that it doesn't have to start with 1 and 1. So for instance, in this example here, we have a Fibonacci-like sequence. It starts with 5 and 5. We add those to get the next one, which is 15. Which is 10, and then we add 10 and 5 to get 15. 10 and 15 gives us 25, and so on. Okay, so same idea behind Fibonacci, we just pick a different starting place. All right, and this, instead of F, we're going to use A. All right, first example, we want to find A11, so the 11th one in this sequence. Why don't you go ahead and pause the video and go ahead and solve this one on your own. Okay, well, let's go ahead and continue out our sequence. We have 1, 2, 3, 4, 5, 6. We need 5 more terms. So if we did 25 and 40, that would give us 65. Let's write this down. 40 and 65 would give us 105. 65 and 105 gives us 170. 105 and 170 gives us 275. And 170 and 275 gives us 445. And let's see, 1, 2, 3, 4, 5, 6. 40 is 6th. 7, 8, 9, 10, 11. So we've got that A11 is 445. All right, now we're going to relate this back to Fibonacci sequences. Okay, given that F25, the 25th Fibonacci number, is 75,025, we want to find A25. So let's compare these two sequences. Well, Fibonacci goes 1, 1, 2, 3, 5, 8, and remember we're just adding the previous two. So 3 and 5 gave us 8, 8 and 5 gives us 13, and so on. And our sequence starts 5, 5, 10, 15, 25, 40, 65, and goes on and on and on. And what we want to do here is compare and see if we can find a pattern. Because if we can find a pattern, then we don't have to just write out the first 25 numbers of this sequence, which is what we want to avoid. We want to do it a little bit of a more clever way. Okay, so we've got 1 and 5, 1 and 5, 2 and 10, 3 and 15, 5 and 25, 8 and 40, and what all of these have in common is that whatever the Fibonacci number is, we multiplied it by 5 to get the number in our sequence. Okay, so we multiply the Fibonacci number by 5 to get our number, right? So 1 times 5 is 5, 2 times 5 is 10, 3 times 5 is 15, 8 times 5 is 40, 13 times 5 is 65. So if we want to find A25, well, let's take F25 and multiply it by 5. So we're going to take 75,025, multiply it by 5, and what we get is 375,125 is the 25th number in our Fibonacci-like sequence. All right, last thing we want to do, express AN in terms of FN. So we want a general formula for AN, and what we're going to do is use this pattern that we identified. So we're going to use the pattern above. So how did we get the number in our sequence from a Fibonacci number? Well, we multiplied it by 5. So we can just write 5 times Fn. If you wanted to, you could also write Fn times 5. Just be sure that that times 5 is clearly not down in the subscript with the n. And there is our formula. That is it for today.